So I'll try to get into the basics of parametric equations today. Let me check. I'm pretty sure. Yep, I hit the recording button, so we are recording. We have a short day, so today we'll get into the basics of what are parametric equations, and then tomorrow we'll get more into why they're useful. I guess I hope today at least you'll see a little bit of why they're useful as well, but tomorrow we'll get into the calculus and how we use calculus with parametric equations, so and why it helps some of our calculus problems. So parametric equations are in some sense a generalization of functions. Well, I guess I should say they are functions when you look in multivariable sense. But our problem with understanding functions at the moment is so much of it is this concept of analytic geometry. We want to study curves. So while we're studying functions, we're really using functions to study curves in space. So relationships between variables. And of course, functions, model relationships between variables, and they have lots of applications in basically every industry, whether it's business, finance, engineering, physics, literally everything, every STEM field. You're going to use functions. So our problem is that a function, this is going to go back, we were testing your knowledge all the way back to the very beginning of functions. Really, what is a function? Hopefully everyone can remember that a function requires only one output for a given input. And it forces us to have an independent variable and a dependent variable. So, of course, our common examples, let's just stick with maybe parabolas. We have y is equal to x squared, and of course, we all know what that looks like. We've got our parabola. And this is since we are back to curves, so it is going to be a graphing topic. So I'll try to make my graphs as nice as possible. I think especially starting with parametric equations, working on graphing and visualizing is a good way to kind of understand some of the intrinsics of what we're looking at and why they're useful. And it will help you with polar coordinates. So there's our y equals x squared. We can have x equals y squared. Oops, this one's going to go sideways, of course. I'll just draw the general shape here. And so we can study these things, we can do calculus on these things. However, we know in both of these cases, we have to have a definitive choice if we model these by functions. Namely, this one, we have to have x as our independent variable, y as our dependent variable. And in the other case, x equals y squared, we actually have to flip that. We have to have x as our dependent variable, y as our independent variable. And so our problem by requiring this independent variable and dependent variable, is what's going to happen if our variables aren't related in such a nice way. Or maybe even if they are, even if we can write y as a function of x, or x as a function of y, coming up with a closed form expression so again, f of x equals some nice algebraic expression for the relationships, i.e. the function, can be difficult. So a couple of examples. In the first case, variables that are related in a nice way, but not in a functional sense. Our standard example is the good old circle. If we have variables that are naturally cyclic in nature and relate to each other in a common cyclic way, so my scale's a little off for this circle. It's going to be a little oblong. If anyone can draw a perfect circle by hand, you're a genius. Apparently this was, I think, Michelangelo. Story my geometry teacher told me in like 8th grade. I think it was the story of like young Michelangelo, right? The Michelangelo who painted the Sistine Chapel. He was like, showed up to some school. I don't know who was it. It was like Leonardo or one of the other guys. And just kind of showed up and like knocked on the door and wanted to apply. And supposedly what he did, you know, they were going to reject him. And he said, no, I deserve to be in your art school. And so he just pulled out a piece of paper, drew a perfect circle, then handed it to the guy. And the guy showed it to like the headmaster of the school or whatever. And then he got in, supposedly, as the legend goes. So if you can draw a perfect circle by hand, you will be Michelangelo one day. So of course, if we have our circle, x squared plus y squared equals r squared, we have a relationship between the variables, but neither can be a function of each, right? If I tried to solve for y, we get square root of r squared minus x squared, but we need the plus and minus, meaning that this is going to be two functions. And we'll get a similar result even if we tried to solve for x. So no matter which variable we solve for, we can't get a function out of it. We have some calculus tools to be able to deal with this if we want to compute derivatives, right? Of course, we can do implicit differentiation. But one of the problems is with implicit differentiation, well, we still just kind of don't have a nice, in some sense, calculus sense of modeling the curve. And maybe I'll expand on that once we actually get to parametric equations. Another example, maybe we'll see this. This is a very classic example in analytic geometry. And it's the, if I can say it, brachistochrone. I forget how to say that. Also known as the cycloid. So I don't know, you think you guys are too young for spirographs, but it's similar to those and how the shapes that are made out of a spirograph. If you don't know what a spirograph is, go to YouTube and just do a YouTube for spirograph. And I can't draw it. So we're starting with something like a circle at the origin. Think of this circle now as a wheel. So think of it as like a bike tire. And right now the bottom of the bike tire is at the origin. And as the bike tire rolls, what's going to happen to this point? If we were to model the path that this point on the tire takes, what's it going to look like? It's actually going to come up and it's going to like roll, it'll increase, it'll come up, kind of be on the top of the tire eventually, and then it'll come back down and it'll hit the ground again. But once it hits the ground, it's just going to keep rolling forward and it'll just bounce back up and keep rolling as this ball, as this wheel rolls around. It'll kind of roll and keep doing that. And so this is a nice function, right? We can actually write y as a function of x, or I guess we can define y as a function of x. Writing it is a completely different problem. And this was something that it took, older mathematicians. I think this is like not 15th, maybe not that old, probably like 16th, 17th century mathematicians trying to model such a curve. And so, of course, it passes our vertical line test. It is a function. Y is a function of x. But the mathematics of actually coming up with a closed form expression, if we had to write y equals some f of x, going to be really difficult to do for something like this, especially because we have this rotating object. And as we'll see, is whenever we have rotating objects, it's kind of nice to measure things maybe in terms of the angle, in terms of theta. So what do? We need a new method. For modeling, how many L's are in modeling? Stupid English. I think there's only one. It doesn't look right. The other word is traveling. Every time I write the word traveling in an email, I think 1L and 2L are both theoretically correct for the word traveling. But Google only likes one. We need a new method for modeling curves. And our idea is to simply consider a point moving in the XY plane as time progresses. And then what we're going to do is model the X and Y coordinates separately. And I say separately, but it's like we're separating the X and Y coordinates, but also kind of keeping track of them together. But really, they're each separate as functions of time. So they are each individually their own functions now of this new independent variable, time. And so this is very much related to this cycloid problem, because we're not just looking at the function now in its entirety. Whereas a lot of times that's kind of what we were doing with functions. When I look at a circle, we look at the entire circle. When we were looking at parabolas, we are studying the entire parabola as a shape. And then maybe we pick out X and Y coordinates, compute derivatives, tangent lines, all that good stuff. Now what we want to try to think of as not only the shape in its entirety, but we also want to think of sort of the shape creating or being created over time. Namely, at time 0, if the bottom of the wheel starts here, or whatever special point we have on our wheel, now as time progresses, we can imagine this thing rolling, and we can watch this point on the wheel travel through space, through our X and Y coordinate system. So that is our method. Any questions so far? Maybe we can draw some generic pictures. The other tool that this gives is it helps us start to broaden our horizons now as we start to move into three-dimensional spaces. I'll talk a little bit about it. I don't think any of the materials for Calc 2 will actually involve three-dimensional spaces, but hopefully everyone will kind of get the sense of how that should start to work. So now, like in R2, whenever I write R2, I just mean the XY plane. We want to think of all of these curves as having some starting position. We want to think of it as the path of some particle over time. So at time 0, maybe the particle starts at a given position, and then it's going to move as time progresses around the curve. And so this gives us a way of modeling a curve such as this, which loops around, loops back in on itself, is clearly not a function. But maybe you could kind of see as well how we might want to try to do this in a three-dimensional space, where now I can have a curve that goes around, under and above, around, and does all sorts of wonky things in perhaps a three-dimensional space. The math in a three-dimensional space versus a two-dimensional space with such a curve and the way we're going to parameterize it, it's actually not much different. We're just adding in one extra coordinate system. And the usefulness is going to come about in the sense that we have one independent variable now, and that independent variable is time. Whereas as soon as we start adding higher dimensions, as you'll see in Calc 3, we like to consider our z-coordinate as a dependent variable, but then we have two independent variables, x and y. And so creating a one-dimensional object, a curve out of that, is kind of difficult. You can't really do it. We can't create a one-dimensional object with two independent variables. You can only have one. And so these parametric curves will help us lead into that, lead into higher dimensions as well. So the way we do this, again, our idea was to model x and y as functions of time. And so the way it's written, we typically write maybe a left bracket, and when we have x of t and y of t. So we're keeping track of what is the x coordinate doing as time progresses, and what is the y coordinate doing as time progresses. And we often sometimes have a definite starting time and a definite ending time. Of course, that has to be the same for both variables. So let's take a look at some basic examples with that. How much time have we got? We only got 15 minutes. So, examples. Easiest one to start with be something like this. And why is this easy to start with? Well, sometimes with parametric equations, we can recover a closed form expression in terms of functional notation. We can write a function y as a function of x in something like this. So, right, if we consider x as t and y as t squared, well, if x is t, we could substitute x in for t in the y. So you should get the sense that this is just y is equal to x squared. But now what does this mean in terms of the parameterization? The best way to graph a parameterization is to make a table and start to plot values. It's always going to be helpful, especially if the functions, the individual functions of x and y are a little more exotic in regards to their relationship to t. So let's just go ahead and pick our values, -2, 1, 0, 1, and 2. X is equal to t, so that one's easy enough. Y is t squared. And so then what you want to look for in terms of graphing this, think of your x and y as the ordered pair. This is literally the ordered pair x, y. So you just graph all of those points as you would if you were graphing in pre-calc. So we've got -2, 4, -1, 1, 0, 1, and 4. And so the overall shape is going to be the same. So a few things that are different, while this is a parabola, first thing to note is we have a definite start and end point. This isn't always the case for parametric curves, but we notice that because we restricted our domain, our time interval from -2 to 2, the only curve that we have is this specific part of the parabola. We don't want to draw it off to infinity like we would with function notation. So of course, with typical function notation, we can define a restricted domain as well. Sometimes that can be difficult to kind of choose the correct points, especially if we have a more exotic looking curve. But the other thing that parametric curves carry is a direction. And not only a direction, a velocity. So the velocity we'll talk more about tomorrow, because as we know so far from calculus, well, what is velocity? It's the derivative of position. So there's going to be some derivatives in there once we get into the calculus of parametric curves, which we'll get into tomorrow. Direction, hopefully, is easy enough. We want to follow the direction with the corresponding flow of time. So time always moves forward. So at -2, we were here. And then we want to consider this curve created by walking in the direction dictated by the equations as time progresses. So of course we started at -2, we kept walking, then at -1 second we were here, 0 seconds, 1, and 4. Our other standard example is to, well, let's move back to I won't say it. We'll see if you guys can guess. You probably can, since we already talked about it today. Let's give a parametrization of x of t, y of t. And let's say x of t is cosine t. And y of t is sine t. And now let's actually not bound our t's. Let's just say t is between minus infinity to infinity, not equal to infinity. Of course, we can't be equal. And so the question is, what does this curve look like? So again, best way to do it, make a table. Time is now our independent variable, so I'd like to keep that one on the left, and then we just have two columns for our x and y. And in helping us plot this, we want to pick nice t values. We want to pick t values that work with the functions. In the last example, we just had polynomials. So polynomials, easy enough to compute integer values. Of course, if we have trig functions, in for sine and cosine, or for our x and y, maybe we're going to pick t values that we can actually compute. So let's pick something like t is 0. Let's pick t is pi over 4, pi over 2, 3 pi over 4, and pi. We'll start with that. Got to remember our trig valuation. So we've got 1, 0, root 2 over 2. We've got 0, 1. We've got, let's see, negative root 2 over 2, root 2 over 2. And we've got minus 1, 0. So let's go ahead and try to plot those. And again, by plotting this, we'll kind of see this notion of the direction and the way we traverse this curve come out of our plotting, especially since we're going to be plotting in the direction of time. So at time t equals 0, my x coordinate is 1. The y coordinate is 0, so we're at the point 1, 0. At time is pi over 4, so a weird value of time, but we're not really plotting time. We're actually just plotting the position of x and y. And nicely enough, the x and y, root 2 over 2, again, not the easiest value, but it is the same. So we know it's going to be on the diagonal. And how big is root 2 over 2? Root 2 is about 1.5. So root 2 over 2, it's about 0.75 on each one. So maybe about here. Then we're going to keep walking, and then we're going to go to 0, 1. Then we're going to go to minus root 2 over 2, root 2 over 2. And then we are going to go to negative 1, 0. What shape do we get?
A circle.
This is our circle. Well known and loved geometric shape. And of course, time, since we're not bounded by any finite time interval, we can keep going. Our next one would be something like 5 pi over 4, which we can compute. And keep going. And as time keeps going, we will get not only the full circle, but we'll get every single loop around the circle. So this is a curve that loops around itself every 2 pi interval of time. And do note that our starting point, at least at time 0, is there. We typically consider time 0 as our starting point, even though we also have negative times. And then we are going around the circle in this direction. And so this wasn't too bad. In working with the circle, with a lot of these past problems we've done with our equation of x squared plus y squared equals r squared, what if we had to do? We have to typically solve for y as a function of x or vice versa. And especially if we're working with other curves that intersect it, we'll have to find intersection points. Sometimes we have to take derivatives. And then what's going to happen if I take a derivative of something like square root of r squared minus x squared? Well, derivatives of square roots, we know, get even more square roots. And then we got this chain rule. And so the derivatives are fairly complicated. Now, I don't know how much you really like trig or anything, but in my opinion, if we're modeling a circle, well, this is kind of nice. By actually separating our x and y variables in terms of functions as time, well, now I just have a nice expression. X of t is cosine t, y of t is sine t. And we'll see tomorrow that taking derivatives is going to be fairly simple. Derivatives of parametric curves is going to simply amount to taking derivatives of the corresponding coordinates. And these functions are pretty easy to take derivatives for, right? They just cycle. We can take as many derivatives as we want and not really bat an eye. Whereas if we had y as a function of x and we were trying to take consecutive derivatives of the circle, those product rules and chain rules are going to get rather complicated, especially after the second derivative. Okay, so one thing to note, and this is a little bit of a problem. So I've been kind of hyping these up a little bit and sort of the niceties of parametric curves, but they're not entirely nice. It is sort of this new mathematical machinery. And in some sense, we're simplifying some things, but also making things more complicated in other ways, right? We're adding an extra piece of information. And by adding this extra piece of time information, it's more complicated in the sense that we have two coordinates to keep track of individually. And we are getting more information out of that, namely our direction and our speed. But along with that, if we were trying to simply study curves as a whole, there can be infinitely many different parametrizations for a given curve. So this can be a little bit of a problem. We introduced this concept of parametrizations. It's helping us study more exotic curves, but we have to be careful on how we study it because now we don't have uniqueness. Whereas typically when we have y as a function of x, there's basically a unique way to write that function in a closed form expression, especially if we perform all of our algebraic simplifications. Not the case in parametric curves. So let's see a quick example, and then I'll turn it over to Lewis and let you guys get started on recitation. I definitely want to give you guys time for the quiz and everything today. Let's just do a similar example. And what's going to happen, let's say I just switch the functions of x and y as functions of t. So if we take a look at something like x of t is now sine t, y of t is cosine t, and let me think about that. Yeah, that's what I want. And again, let's just have t unbounded and try to plot this again. Well, hopefully you can kind of see that the relationship between the given variables is essentially the same. We just changed the order of the variables in some sense. So we should get the overall same shape in the XY plane. So let's just try to figure out what's going on here, what's different about it. So we have our t, our x, and our y. We go 0, pi over 4, pi over 2, 3 pi over 4, pi. And then that'll give us a good enough sense of what's going on. So now our x coordinate is going to be 0, root 2 over 2, 1, root 2 over 2, 0. Y is going to go 1, root 2 over 2, 0, negative root 2 over 2, and 1, negative 1. So let's plot those coordinates in time. And now at time t equals 0, we are at the point 0, 1. So we are up here. As time grows, we are at root 2 over 2, which is over here. At pi over 2, we are down at 1, 0. Then root 2 over 2, negative root 2 over 2. So the y coordinate's negative in that case. And then at pi, we are at 0, negative 1. So if we were to keep going in time, hopefully everyone can see, we still get a circle. However, how are we traversing this curve? Now, our starting point was here at the top, and we're traveling clockwise. So we're actually traveling in the opposite direction.
So is that kind of what you mean about velocity?
Exactly. So now we've got this extra stuff to keep track of, which can help us for certain physics problems when we actually want to keep track of how the particle is moving in time. This is going to be really useful. For studying the shape as a whole, it kind of just is an extra thing that we have to keep track of. Because in the previous example, our velocity was going around this direction. So a velocity, as we will see, it's what's called a vector. So maybe I'll introduce that a little bit tomorrow. But our direction of travel, so think of velocity as something like wind direction. Anytime you're looking at like a golf match and they measure the direction of the wind, it has to have a certain direction and a magnitude. It blows with a certain strength. And so we will see this. In this case, we're traveling to the right or counterclockwise from our starting position at a certain speed, whereas in the other parametrization, we were going in the opposite direction. And then we could also potentially adjust the parametrization. So maybe on your own, try to check out what's going to happen with this circle if now we simply adjust the argument by a factor of 2. Again, the same relative relationship between our coordinates, between our x and y functions, is going to hold. So the overall shape is going to be the same. We're still going to get a circle. But what's going to happen with this is, in some sense, it's almost going to make time look like it's moving twice as fast. In other words, we're going to be moving around the circle twice as fast as we would with this parametrization. So velocity is going to give us a direction of travel as well as a speed of how fast we're moving. And so we'll take a look at how we can determine these things a bit more tomorrow. Any questions?